Hi, this is Shelley Physics episode on moving charge in a magnetic field. Yes, B stands for magnetic field. Today it's brought to you by Inigo Montoya. You killed my father. Prepare to die. No, that's not a threat. It's a movie line from The Princess Bride, arguably the best movie of all time. You should watch it. So anyway, back to magnetic fields. If you were watching my last lesson on introduction to magnetic fields and such, you might remember that a magnetic field can be created with a coil of wire and running a current through it. So a current is moving charge. So with this loop, the wires surrounded by or coated with an insulating enamel, which keeps that charge flowing through the loop. Now I'm going to hook up a battery to it in a moment, and the current will go up through the paper clip into the loop, flow around the loop, and back down the other side to the battery. So nothing's going to happen until, even when I connect it, until I put a magnet nearby. Sometimes it's a little bit off, but this is the principle of how motors work. Now this is a broken motor because I shaved the wire in places I shouldn't have shaved it. But you see that the loop is interacting with the magnet. It's moving back and forth and flipping direction. It just flipped and changed direction. It's a little confused in spots. I might even be able to direct it a bit and make it face a certain direction. Okay, so there's obviously an interaction here between the magnetic field of the bar magnet and the magnetic field of the coil. So what you're seeing here is a principle. It's a law of nature that moving charge interacts with a magnetic field. And the only things that interact with magnetic fields are other sources of magnetic fields. So both of these are sources of magnetic fields, a bar magnet and a coil, but that coil must have, you see it's disconnected here, that coil must have current flowing through it. Otherwise, there's no magnetism that's occurring at this point. I just pushed it by touching it. So I'm going to take this away and talk about this. Now, what do you think affects how a moving charge might be affected by an electric field? Do you think moving the charge faster or moving it in different directions or angles would have an effect? Those are some good guesses if you had them, and you're exactly right. So let's say I hook up the two ends of this coil to a battery, and we would have current flowing, let's say, in the counterclockwise direction. That would create something we're going to learn about later, is that would create a magnetic field. So what if I pass a charge, let's say a proton, in this direction, right by that magnetic field? What would happen to it? That's what we're going to answer here today in today's lesson. All right. So to begin with, a little picture. We have a moving charge, and it has a velocity vector. Now, if that moving charge passes through a magnetic field, so I need to draw a representation of a magnetic field. So I'm drawing an area of space that this positive proton, this charge, is going to pass through, where it's going to interact with a magnetic field. And that's what B stands for. While I'm introducing the symbol for magnetic field, I'll also introduce the unit. Magnetic field in standard SI units is the Tesla. Tesla! Yes, that's where we get the Teslas. Check out I think there's a good epic rap battle of history on Nikola Tesla and Thomas Edison. Beware the content, though. Can't always count on those. All right, so what's going to happen to this positive charge as it passes through the magnetic field? Well, if it's got a velocity to the right, it's going to remain going to the right until it gets into that field, and then something happens to it. A force is applied to it. So an electric field will apply an electric force to a charge, whether it's moving or at rest. But a magnetic field will not apply a force to a charge unless it's moving through that field. So the amount of charge does have an effect on the magnetic force applied to that charge, and its velocity also has an effect. If zero velocity gives zero force, then a greater amount of velocity, greater magnitude of velocity, will give a greater amount of force also. In addition, do you think the strength of the magnetic field would have an impact? Of course. And if we are talking about something like a magnet, okay, a magnet won't generate a uniform magnetic field like this. It acts sort of like a positive charge. The magnetic field would be pointing out in all different directions and spreading out. Those lines would spread apart, so the field would be weaker further away from the magnet and stronger closer to it. So that those varying directions of the field lines and the intensity of the magnetic field would have an effect on how strong this magnetic force on the moving charge is. But what we've got here is something more like a horseshoe magnet, something in between, where if we've got the north side down below and the south side up above. So that's this kind of field here. Or if I position the horseshoe magnet sort of like that, that would be the field, approximate field of that positive charge passing through that region. So back to it, we've got the moving charge, has velocity, and it passes through this magnetic field. So force should be proportional to charge, proportional to velocity, and also proportional to magnetic field. But the thing is, magnetic field and velocity are both vectors. They have direction. So we're multiplying these two together. So how do they interact? Well, it turns out, and this is just the fundamental nature of charge, moving charge interacting with a magnetic field, is that parallel components of velocity and magnetic field have zero effect on the force that's applied to that moving charge. That's right. So if the parallel components of V are zero, guess what? The perpendicular components are non-zero. So what we have here is a multiple of two vectors. We have a vector product because it's the perpendicular components that do interact. So it's important to note that we do have a vector product that's going to happen here. There's going to be a direction to this force. Force, this is the other clue that it's got to be a vector product, not a scalar product. It's because force is a vector also. And a scalar product like a V dot V would give us a non-vector quantity. It wouldn't have direction. So what would happen? What can we estimate the direction or guess at the direction this is going to travel in? Well, because it's V cross B, I put those in the order that goes along with the fundamental nature of this force. That if we have a positive charge, positive Q, traveling in a direction that's at least has perpendicular components to the magnetic field, then we need to take V cross B, which means if we start with our hand, like in the last lesson, the right hand rule, start with the hand in the direction of the velocity, our palm facing the direction that the magnetic field is facing, so that we can rotate our fingers like this in the direction of that field. So V cross B, then the force is going to be up out of the page. This particle is going to travel up out of this paper toward the camera there. All right, that's the direction. How do I show that? How do we show the direction of this force, the direction that this particle is going to accelerate? Well, if you consider an arrow in general, the arrow has a point to it, and an arrow shot from a bow has fletching. There's feathers that kind of come out. And sometimes if you look at an arrow from the front, it looks like a point. Or if you look at an arrow from the back, you see the fletching, which makes kind of a crisscross pattern. So in physics, when we're talking about three-dimensional space with a two-dimensional paper, we use this symbol to represent the vector direction out of the page, or up. All right. Now on a paper, sometimes we say this is up and that's down, but the paper is in a plane this way. So we sort of have an X direction, a Y direction. So up would represent our Z direction. Z direction. Okay. And the X would be into the page. And those are the best ways to describe it, really. Into the page or out of the page rather than up or down. You know, up and down, left and right, those can always be relative. But when we say into the page, out of the page, those are relative to the page. It's the best way to describe it. So we could also say down or in the negative Z direction. Okay, this would be a positive over here. So there we have it. Our force, the force would be up out of the page. Okay, so let's look at a couple more examples and directions. It's good to see this visually. What if we have a magnetic field in this direction? B. Okay. And now we're going to take a negative charge, let's say an electron, as a velocity in this direction. Now what's going to happen now? Well, consider magnetic force equals QV cross B. All right? So what's it going to be here? Well, the V cross B is going to be the perpendicular components of V and B. And I'll get to the IJK example of that in a moment and put some numbers to this. But we have an electron in this case. So what's it going to do compared to a proton? It's going to react opposite. So if a V cross B makes the positive go out of the page, like in the first example, makes the positive charge go up, what's the same or similar kind of V cross B going to do to an electron? It should make it go into the page, the opposite way. So if we first take V cross B, again we're going to take V and face our palm in the direction that the arrows are going. Now, the arrows don't have to be exactly perpendicular, they just have to be facing up. Okay, you see that? So the result of V cross B is going to be a direction perpendicular to the plane of velocity and the magnetic field. You hear that? If you didn't pick up on that part about the cross product, is if you put the vectors V and B in the same plane, then the resulting direction is either going to be up out of that plane or down into that plane. It's always going to be perpendicular to that plane of the two vectors. So the V and B are still in the plane of the page. So V cross B is still going to be up out of the page. However, this is an electron. So with this Q, there's going to be a negative aspect to a positive K hat. Okay, the K hat is referring to this positive Z direction. J is for the X direction. I'm sorry. I is for the X direction, J is for the Y direction, and K is for the Z direction. So the V cross B is going to give us a positive K, but with the Q, we're going to have a negative tacked onto that. So a negative times a positive would give us some number, whatever those values multiply to be, times a negative K direction. And the negative would be down into the page, right? That would be in this direction, okay? So instead of like a right-hand rule going this way, it's going to be going kind of down. I'm not really talking about the Q cross V here, but the direction of the negative charge is going to be opposite of the positive. So the force will be downward. It's going to be accelerating downward, kind of have a curved path going into the page, just like that. All right, let's get more of a numerical example of that. Actually, I like that one. Let's flip back to that. Let's say the angle between that V and the B, the magnetic field, is 30 degrees. Okay. We'll give Q 5 times 10 to the negative 6 coulombs. It's 5 microcoulombs. We'll give the velocity at a cool, let's say, 20,000 meters per second. Okay, we're traveling along here. Very sublight speeds, okay, but still pretty fast, 20 kilometers per second. That's a good speed. And magnitude of the magnetic field. Let's put our vector symbol on here. Let's go with 100 milliteslas. All right, and that's equal to 0.1 teslas. All right, so what would be the magnitude of the force on this goober here? So the magnitude of the force would be Q V cross B. Right? Now we're given the magnitude of V and the magnitude of B. So how to solve a cross product given the two magnitudes? Well, we're going to first plug in the scalar quantity in there. The Q is 5 times 10 to the negative 6. And you might recall that the definition of a cross product, A cross B, two vectors, is the magnitude of A times the magnitude of B, sine of the angle between them. We should make that a phi or phi. They're both acceptable, phi or phi. Just don't be a faux or fum kind of person, okay? So AB sine theta is the, or phi, is a definition of the cross product. So I'm going to take the magnitude of V, 20,000, times the magnitude of B, 0.1 teslas, times the sine of the angle between them. Okay? So this is going to give us actually the magnitude of A cross B, not the direction. Now if there was a negative here, that would indicate what to do with that direction. But thing I like about sine 30 is it's equal to 1/2. So I've got a 10,000, 1/2 of 20,000 is 10,000, and a tenth of that is 1,000. So I'm taking 1,000, or 10 to the third, times 5 to the negative 6. So that will give us a 5 times 10 to the negative 3 newtons, or we could say 5 millinewtons of force. That doesn't sound like a lot, but on something like a proton, that's a lot of charge. Or even more so, if I am dealing with this case, what if this were a negative electron? Then we would have had a negative there and a negative 5 millinewtons on a super duper tiny, little tiny mass. Yes, I had lots of tinies in there. Now this negative would be applied to the direction. Okay, we've got a negative with a force, so we have to keep that in mind. Let's apply that to the direction now. So if this were a positive charge, V cross B would be positive, going up out of the page. But applying the negative, we'd have down into the page. So the force, magnetic force here, as a vector, would be 5 millinewtons in the negative k direction, down into the page. Be the best descriptor for that answer there. Okay. Now what if we do have a new Q? Let's just say we'll take the same amount, microcoulombs. New example here. I'll call this example 2, even though I didn't label the first one. And let's take a velocity vector. We'll have it in the ij direction. I'm just making one up in my head here. 2i hat minus j hat. Okay, so it's got some x component and some negative y component to it. Say the magnetic field is also in that plane. You know what, let me make this in the xz plane. X in 5K. Just for a little fun here. We'll conceptualize this in a moment. So what would be the magnetic force then with a V cross B? Well, we would have that 5 microcoulombs. I'm going to make it a positive this time. We've got a positive charge. 5 times 10 to the negative 6 coulombs. And then we've got this V cross B. So here we're taking the cross product or the vector product, keeping in mind that I cross I is 0, so any components that are parallel is equal to 0, and keep the example that I cross j is a positive 1k. And I like to go back to this tool if you've never used it. Just write ijk, ijk. It doesn't mean I'm just kidding, it's the order. Okay, so ijk, ijk. We'll come back to that in usage if you haven't seen it use that before. Now we're going to take the velocity. So for the velocity, we're going to take 2I cross I, 2I cross 5k, negative j cross I, negative j cross positive 5k. I could write it like an algebraic expression. This is a little bit faster. So we're distributing some algebraic numbers here, algebraically. So 2I cross I is 0. 2I cross 5k would have a magnitude of 10. And I cross k, forgot a piece to my tool here. If I go I to j, I'd get positive k, so ij is a positive k, so going to the right is the positive direction, whereas j cross I would be negative k. Well, in this example, we've got I cross k, so to go from an I to a k, going to the right doesn't work, but going to the left does. I cross k is j in the negative direction. So we've got a negative j there. That was 2I across 5k. Now I go to negative j across I. So that's a negative 1 times a positive 1, which is a negative 1. And so I already used the negative. So you gotta do this your own way. I like to do the coefficients, keep them separate from the directions. So I've got a negative 1 already. So now I have a positive j cross a positive I. J cross I is a k, but in the negative direction. So I would have a negative k there. You see how that negative and the negative is going to cancel out. So I just did 2I cross I, 2I cross 5k, negative j cross I, and now I do negative j cross 5k. So negative 1 times 5 is a negative 5, and j cross k is positive I. All right. So here we go. We have 3 different terms here. All of them will be multiplied by 5 times 10 to the negative 6. So our force is going to be 5 times the, I'll keep the negatives in my direction, I like doing that. 5 times 10 is 50, and can't forget our 10 to the negative 6, with a negative j tacked on there. So that tells us the point in the negative j direction. And we have a positive k here, times 5, so plus 5 times 10 to the negative 6, just multiplying that by the 1, and a positive k. And we have a 5 times 5 is 25 times 10 to the negative 6. Keep them all in the same order of magnitude there, just so they're comparable. And let me check out the direction. I have a negative applied to that, so a negative I direction. So just put all these in the more of the order, IJK order. We'll have a positive 25, so negative 6 in the I direction. Then we'll have this 50 times 10 to the negative 6 in the negative J direction, and 5 times 10 to the negative 6 in the positive K direction. Okay, so those are components. This vector is completely perpendicular to the plane of these two vectors. And if we could put those two into a plane, it'd be more of like a diagonal plane. So we are going to get a diagonal force out of it. Kind of a funky look to it, but that's how you'd use our new tool here. Force on a moving charge using IJK notation. Last thing I want to talk about is maybe just a few more visuals. Let's take an area, and with these visuals, we're going to predict the path of a moving charge through them, through these magnetic fields. So if our magnetic field is out of the page, and we've got a positive charge passing into this region, what would we do? Take our right hand and point it in the direction of that moving charge. Now I need to face my palm towards the direction of the magnetic field, which is up, and then curl my fingers towards it. Wait a second. Something going on here. Oh, yeah. So, let me do that again. So we take the, yeah, I get a little confuse myself sometimes. This can be a little confusing, spatially, it's kind of confusing. So anyway, break. I'm going to take my hand, put it in the direction of the moving charge, and twist myself around here. And I need to rotate my hand towards the little speck there, towards the direction of the magnetic field. Rotate my fingers that way, so that's the direction of the magnetic field. And my thumb here, if I could rotate it correctly. And this is going to be easier. Oh, that's a lot easier. Okay, let's try that now. Whew. That's the direction of the charge. Rotate my hand. There's the direction of the magnetic field. So the force is going to be that way of my thumb. So it's toward the bottom of the paper, downwards. So the force is going to be downward. So once this positive charge enters this region, it's going to start to accelerate in that direction. That might be the path. All right, sort of like gravity right there. All right. Now, what if this were a negative charge? What would it do? Well, as it approached, it would do the opposite. Okay, we do the right hand rule the same way. There's a direction of the charge. I'd have to rotate my hand towards the direction of the magnetic field. I can point my fingers that way appropriately. And look, my thumb is also pointing downward to the bottom of the page. But this is a negative charge. So instead of going towards the bottom of the page, it's going to go towards the top of the page. It's going to be forced. This is a force on the positive. The force on the negative charge would go up. So its path might be more like that. All right? So that's just a few more examples. I'll give one last one here. Let's take a magnetic field, since I haven't done into the page yet. I'm going to try to be a little smarter about the pathway of this particle. Now I'm going to take a positive charge moving this way. There's the direction of its velocity. So what's it going to do? So I take my hand in the direction of that velocity, and I need my palm facing the direction of the magnet. I didn't label that. Facing the direction of the magnetic field, so that's downward. So that means the velocity is going to be in that, the force is going to be in that direction, perpendicular to the velocity and the field. So the force is going to be in that direction. So when it enters this region of space, it will start to curve and accelerate in that direction. That's going to be its path. All right. So I hope that was helpful. Example of cross products using the right-hand rule and learning anew about how a magnetic force is placed on an electric charge that's moving, and it has to be moving. Notice one little key element here. If the velocity of the charge is 0, what's the force? 0. So a static charge is not affected by a magnetic force, but a moving charge is affected and forced by a magnetic field. Okay, I hope that was helpful, and take care. Go watch Princess Bride.